Hey everyone, in this video I want to cover two things. The first is determining the size of a sample, and the second is showing you just a few little tricks with Excel or Google Sheets that you can use to simplify and make finding confidence intervals as well as this sample size estimator a little bit quicker, just using some of the built-in formulas and functions to kind of work through it. So let's start with finding the size of a sample. So we did confidence intervals in the last video. This economist wants to estimate the mean per capita income. So he wants to know how much money people are making for a major city in California. He believes that the mean income is $21.40 and that the standard deviation is known to be $9.20. And I don't know if that's in thousands, so it's really $21,400, and $9,200 is the average and the standard deviation. So he wants to say how large of a sample would be required in order to estimate this at a 90% level of confidence with an error of at most 55, in this case it looks like 55 cents, but $550. So round the answer up to the next integer. So the things that I see right away in here is that I have a standard deviation. In this case it talks about this standard deviation is known to be $9,200. So I've got a standard deviation of 9.2. Right? I also see that the error he is looking for is 55 cents, or we're just going to call it 0.55, because it really doesn't matter what we're talking about, and he wants a 90% level of confidence. Now, I showed in confidence intervals that we use these critical values. In this case, the formula that we're going to use is going to use the Z critical values. So finding critical values of Z, these would always be the same, maybe rounded off a little bit differently. But the critical value in this case is 1.645. Again, you'll notice that I have a Z alpha over 2, which talks about it being two tails. Whenever we're talking about a confidence interval, two tails, high end, low end. So I've got a critical value of 1.645. Now that's the information that I am going to need in order to figure out or estimate the sample size. To find the sample size, the formula is we are going to take this Z value, the critical value, and we are going to multiply it by the standard deviation divided by the error that I'm looking for, and then we are going to square all of this, right? So in this case, I am going to have n is equal to, and I forgot to look at what that was, 1.645, that's the critical value, times the standard deviation of 9.2 divided by the error of 0.55, and I am going to square all of this. So let me crunch those numbers in a calculator here. So I typed these things in. I use Excel as my calculator. 1.645 times 9.2. That quantity is divided by 0.55, and then that entire thing is squared. And my result is 757. And I'm always going to round this up because I can't use less than 757. I have to use more, and I can't have 0.15 people. So I'm going to say that this is 758. So that is the sample size that I need to have in order to have that 90% confidence interval with an error of about $550. Now the next thing I want to show is how I use Excel, or Google Sheets in this case, to do a little bit of this work for me. So as I'm looking at this, here's one of the problems that we did in the last one where I'm going to do some sort of confidence interval. Now what I do is just have a place where I will record the things I need for a confidence interval. The average, standard deviation, the sample size, and the critical value. These inputs right here I actually type in. Whoops. So let's just show that those are typed in. These things are figured for me. So I don't type in anything there, but I do have some formulas, and I will show what they are and how I did it. But in this case, the mean for this is 15.7. The population standard deviation is 2.3. And I have 1,097 families that is being sampled, and it wants me to construct an 85% confidence interval. Now, this critical value is based on whether or not you know or don't know the standard deviation of the population. In this case, the population standard deviation is 2.3, so I know it, which, if you recall, meant I use a z-score. Critical value. So in my tables over here, since I've got them right here, the standard normal table critical value for an 85% two-tailed, remember, A over 2, alpha over 2, I'm going both directions, is 1.44. That's the critical value that I use here. And recall that if I were using a t-table for this, if I didn't know, in the t-table, I would have to go down to 1,097 families. So in this case, I would probably use 1,000, since that's as close as I can get to it. And that would be the degrees of freedom. And in this case, I would have also had to find an 85%, which they don't list on this one. I've got an 80% and a 90%, so I don't have an 85% in this t-chart. Some may use it, but I would find my t-value. I could use the same thing here. Remember, in both cases, it required you to take that critical value times the standard deviation and then divide that by the square root of the sample size. That is what this margin is doing. In this case, if I double click it, you're going to see that it is taking B4 times B2 divided by the square root of 1,097. So I put that formula in once, and I'll do it again here, equals B4 times B2 divided by the square root of 1,097. That formula is entered, it will calculate that. That margin gets added and subtracted to and from the mean. So the low end, you'll see, is the mean minus this number, and the high end is the mean plus this number. Now, I did it a little bit backwards because I was developing this as I went along, but the simplest way to do this would just to say that this one is going to be the mean minus that margin that I have, and over here I have the mean plus that margin that I found. And you will see the same results there. Then you could worry about rounding it. Now, the key things here is, remember that you have to have a standard deviation. Sometimes they give you a variance and you have to calculate that. But that's how I use that, so that I can jump through some of these problems and say, and let's try it again. In a case like this, I've got 25 samples. The mean is 0.502. And you'll notice these numbers changing as I do this. The standard deviation is 0.0313. And notice that this is the sample data has a standard deviation. I don't know what it is for the population. So in this case, I would have used a t-table, area and two tails. I'm going to find a 98% error, and I need a degrees of freedom of 24. So 2.492 would be my critical value. It calculates the margin and then the low end and high end for that confidence interval. Now, I do something very similar when I'm working with the error. If you were to recall, that error formula really had us use the critical value in that last problem that we had, and I'll bring that up over here. In that last problem, I needed to know the critical value. In this case, it was 1.645. I had a standard deviation of 9.2. And in this case, I needed to know the error of 0.55. Now, once again, I can create that formula all at once so that I can just type those numbers in and then look here for the error. So the error formula was taking the critical value, and I'm going to put parentheses here right away. I know I'm going to need it. I'm going to take the critical value times the standard deviation divided by the square root. Oh, excuse me, not divided by square root, divided by the error. So that's this part, and then I am going to square the entire thing, and you'll see that as I change some of these problems, I will be able to say like, oh, what if the mean was 10 and the standard deviation was 3 and there were 43 of them and I had a critical value of, let's just keep it at 1.645, I would need a sample size of 81. So that's how I use Google Sheets to just make my own little calculators, save that, or recreate it so that you can kind of jump through a bunch of these if you needed to. But that is how to determine the sample size, as well as how to use Google Sheets to do the confidence intervals and the sample size based on the error as well.